Welcome to all. Today's lectures we are going to discuss the new topic stereochemistry. In these topics, now we have learned the geometrical isomerism. You know that stereochemistry or stereoisomerism they can exhibit various isomers having the same structures but different their spatial arrangement. And hence this shows different configurations are possible. So two types of stereoisomers are there like optical isomer and geometrical isomer. Firstly, we are going to learn geometrical isomers. Geometrical isomerism it may be characterized by various compounds having these carbon-carbon double bonds because their molecular symmetry and the compounds they do not rotate the plane of polarized light. We have seen that is two similar groups on the same side which is called as a cis isomer, and these similar groups which is opposite side of the double bond is called as a trans isomer. For example, in these molecules this is two groups which are similar, is two groups which are similar on the same side which is called as a cis isomer. In these other general examples, it is also the two groups which are in the same side, so it is a cis isomer. It is a different isomers, they will have different group, so it is various isomers. So we have seen these examples. So on the same sides, these hydrogens on the same sides, so name is cis-2-penene, so cis compound or cis isomer. But in these examples, which are the similar group which are on the opposite side, so it is named as trans isomer or trans-2-penene. Now, the number of geometrical isomers we can calculate by using the formula as 2 raised to n, where this n is the number of double bond. For example, these molecules they will have two double bonds. Therefore, 2 raised to 2 is equal to 4 isomers are possible. So these 4 isomers are like this 1, 2, 3 and 4 isomers. And those 4 isomers we can find out which is cis and which is trans. Now these first examples we are see is here. These first examples it is cis because these two atoms which are similar on same side, so it is cis. Second, carbon-carbon double bond it is also cis because this similar group which are on the same side, so this is cis. Now second examples we see is here, it is also cis. So first carbon-carbon double bond they are cis because similar group which are on the same side. But other carbon-carbon double bond these are trans due to these similar groups which are in opposite to each other, and therefore third double bond is cis, second double bond is trans. Now third examples or third isomers we have C here. So first carbon-carbon double bond which are trans to each other because the similar group which are trans to each other or opposite to each other. Therefore it is first carbon-carbon double bond is trans. Second carbon-carbon double bond they will be cis because the similar group is on the same side. Therefore it is cis. Now this and fourth isomers, the first carbon-carbon double bonds they will have the trans due to the similar groups which are in the opposite. which or other carbon-carbon double bonds also have these two similar groups is on trans to each other or opposite to each other. Therefore, those isomers show first carbon-carbon double bond are trans and second carbon-carbon double bond they also trans. Now, we have see in this aldoxyme. Aldoxymes also they shows we compare this hydrogen and hydroxyl group. They are on the same side of the double bond. The prefix we are use is C. And they are opposite. This is called as a anti. So first oximes, then we will show these hydrogens and the hydroxyl. We compare so this hydrogen, this hydroxyl, they are on the same side. So prefix we are use C. C, the benzyl dioxide. Similarly, second examples, the hydrogens and this hydroxyl group which are on the opposite side. So prefix we are use anti. So this anti-benzyl dioxide. Other examples, now C is here. This is the other group like this, the methyl and this OH is on the same side, the word we are using. And this CS3 which are lower groups than pH and this OH which are in opposite. So word we are using anti-methyl ketoxide. Now next types of the isomers we have seen the geometrical isomers also shows by the cyclic compounds. Cyclic compounds having a rings which is placed the rigid double bonds as well as they restrict the rotation of the carbon atoms of their axis. Now we have C is here these cyclic compounds. The two similar groups on this above the plane or two similar groups which is below the plane. This is called as the cis compounds, and two similar groups which are opposite. It means that one is above and one is below. That time this is called the trans isomer. So first ring, that is this cyclobutane ring. So name is 1, 3. 1, 2 and 3 positions. 1 and 3 positions have carboxyl group. So 1, 3 cyclobutane dicarboxylic acid. But two groups, it is carboxyl group and this carboxyl group which are on the below the plane of the ring, and two protons which are similar they are in above the plane of the ring. So this is a cis compound. म्हणजेच इथं हे आपण जशी ही रिंग आहे बघा सायक्लोब्युटेनची रिंग, जर आपण अशी प्लेन पकडली, प्लेन कन्सिडर जर केली तर हे दोन कार्बोक्सिल ग्रुप आहेत, हा एक कार्बोक्सिल हा एक कार्बोक्सिल कसा असणार आहे, ह्या रिंगच्या खालच्या बाजूला असेल आणि हे दोन हायड्रोजन असतील ते कसे असतील, ह्या रिंगच्या वरच्या बाजूला असतील. म्हणजे दोन सिमिलर ग्रुप हे रिंगच्या खालच्या बाजूला असतील किंवा रिंगच्या वरच्या बाजूला असतील तर आपण त्याला सिस कंपाऊंड म्हणतो. आणि जर हे दोन सिमिलर ग्रुप म्हणजे दोन हायड्रोजन आहेत हे जर एक खाली असेल आणि एक वर जर असेल तर आपण त्याला ट्रान्स म्हणतो. सेकंड बघा, सेकंड कंपाऊंड मध्ये किंवा सेकंड स्ट्रक्चर मध्ये क्लिअर दिसतंय, दिस इज कार्बोक्सिल ग्रुप्स which are above the plane and these carboxyl group they are below the plane and therefore these compounds are trans compounds. Other atoms we are compared like these hydrogens are below the plane of ring and these hydrogens are above the plane of ring, therefore these compounds are trans. Similarly is a cyclohexane ring, they also shows the geometrical isomers as like these both methyl groups which are is below the plane of the, therefore it is cis. These hydrogens also above the plane of the. But these two hydrogens are below the plane and these two methyl group are above the plane. This is also cis. But similar groups is on opposite, that is one is below and one is above. See here, similar group like this methyl group is below the and other methyl group which are above the ring. So this is trans. Similarly, other atoms we are compared like hydrogens. These hydrogens, so one hydrogen is below the ring, second hydrogen is above the ring. So it is a trans compound. Now next terms we have discussed the optical isomerism. Optical isomerism, it is isomerism, they having the same structures but different configuration. Their molecular asymmetry, the compounds rotate the plane polarized light. Optical isomers have the similar chemical properties, but different the plane of polarization. Optical isomers are the rotate the plane polarized light are equally but in opposite direction. And hence plane polarized light contains the various vibration can be done. So nucleus prism are mainly used for the collecting all these polyvibrating light. And this light is said to be polarized light. For example, these ordinary lights will have the ray of various light. They can vibrate in any one direction which are perpendicular to its path of propagation. And then this light which is passed this Nichols prism. So plane of polarization can be done through a Nichols prism by immersing the light in this vibration. Only one plane such as light is said to be polarized light. The prisms are obtained polarized light is called as a polarizer in one plane. It is called as a plane polarized light. This is a ordinary light which are polarized in any one direction, but Nichols prism are mainly used to convert plane of polarization having one direction. Now we have see optical activity. For example, this plane of polarized light can pass the solution containing organic substance like glucose, lactic acid. The light get rotated at a certain angles. So this property to rotation of this angle we can measure by various organic substances, which is called as optical activity. For example, the light is polarized and it rotates to right side. This is called as a right or left side. This is called optical activity, which can rotate the right side. This is called as the dextrorotatory, and which is rotate to the left side, which is called as the levorotatory. And therefore, total rotation depends on the number of molecules and hence the concentration of the solution. We can find this rotation, that is alpha, is equal to theta upon L into C. L is the 1 decimeter in length. C is the concentrations as about 1 gram per ml. So this type of the mechanism can be done. This light coming from Nichols prism, like plane polarized light, which is passed through this glucose solution or organic solvent or organic compounds, and then after this light can shows as light. It is rotate from left side or the right side, which is depends on the plane of polarization by the compounds. But the compounds can show optical activity. They shows optical isomerism. The compounds may rotate the plane polarized light in the different directions or by different angles, or it may be different sign of specific rotations. That is, the isomer which rotate the plane polarized light to the right hand side, or it is a clockwise, it is called as a dextrorotatory and denoted as the plus sign, and anti-clockwise or left side rotation, it is called as a levorotatory and to indicate the sign negative. Optical isomer shows molecules having the same asymmetric center or the chiral carbon. Chiral carbon is the carbon they attach the four different group. This is called chiral carbon. So this is a chiral compounds and this shows star. So this is four chiral, four different group. This is one, this is carboxyl. Second is a hydroxyl. Third one is a methyl. And fourth one is a hydrogen. So four group which are different attached to this carbon is called chiral carbon. And hence number of optical isomers also we can calculate by using the formula is 2 raised to n. Here is only one asymmetric center, so there is two isomers are possible. So one is this, the dextrorotatory, and one is levorotatory. So but both are the isomers with each other, right? Now next points we have discussed the chirality or the dissymmetry of these molecules, which is defined as the property by which a molecules they cannot be superimposed on its mirror image, or all the atoms and bonds object do not coincide with those in the mirror image. This is called as the chirality. For example, if the chiral molecules exist as non-superimposable mirror image. Chiral molecules can exist non-superimposable mirror image of each other. Is called as the anisomer, and the phenomena is called as the anisomerism. See, yes, this is a lactic acid. These lactic acids are L, this means levorotatory lactic acid. We can take this mirror image of this mirror image as like this D lactic acid, and this is a L lactic acid. So this dextrorotatory and this is levorotatory, they are non-superimposable mirror image. Now we have see other examples like tartaric acids. Tartaric acids has the two chiral center, which is two. This is the one chiral center and second chiral center. So therefore, it is four isomers are possible. But out of these four, the two is one is D, other is L dextrorotatory, levorotatory of tartaric acids, which are optically active, and other is a mesotartaric acids, which is optically inactive. Optical activity of the molecules, they are property conditions of the chirality or the dissymmetry of the molecule. Now C is here, so two chiral centers, so four isomers are possible. But out of these four, the two is identical. So this is one, this is a two, and this is a three. So this third molecules or third isomers, its mirror image are identical and therefore it considered as only one isomer. So these isomers, they will show two chiral centers. It is a plus and minus tartaric acid, right? This is a plus, this is a minus tartaric acid, which are optically active because we are passing this plane or cut these molecules which are not superimposable mirror image. Similarly, this example for these molecules, we cut these molecules, these parts and those parts which are not superimposable mirror image. Therefore, it is optically active or it is not present any plane of symmetry. But mesotartaric acids are optically active because it is present the plane of symmetry, because we cut the molecules on this manner, so these parts and those parts which are similar to each other. This is therefore mesotartaric acid is optically inactive, and hence so those molecules which are must be chiral or dissymmetric because they must be non-superposable on its mirror image. The molecules will be chirals. The molecules will be chirals. They containing three elements are absent, like the plane, center, and axis of symmetry. If one element is present, the molecules will be superimposable on its mirror image, and therefore such a molecule do not shows chiral, optically inactive. For examples, so those molecules we have seen is here mesotartaric acids. Mesotartaric acid has the plane of symmetry. Mesotartaric acid has plane of symmetry. We have seen previous slides like this. The mesotartaric acid is a plane of symmetry and therefore it is optically inactive. It is a dissymmetry. Hence it is a achiral or it is a dissymmetric optically inactive molecule. Now we have discussed some stereochemistry of carbon compound containing the one asymmetric carbon atom. You know that it is a one chiral carbons, or you know that chiral carbons having a 4 different group is attached. This is called as a chiral carbons. Now C is here. This is a one chiral center. Therefore, two optical isomers are possible. They forms relate to each other which are non-superimposable mirror image. One of them represent the dextrorotatory and one of them represent the levorotatory. We can rotate the plane polarizer light to the right and other which is a levorotatory. We rotate the plane polarizer light towards left side. So these two molecules, this is one molecules and these molecules which are non-superimposable mirror image. Non-superimposable, these molecules which are, some mistake is there, this is AOH. This is OH. Okay. So these molecules which are non-superimposable its mirror image and therefore it is a present chiral centers. So this is chiral center having a 4 different group and they shows one of is a dextrorotatory and other is levorotatory. Similarly, these molecules they also shows this mirror image of each other And these mirror image, they are non-superimposable mirror image. For those molecules also, these molecules also non-superimposable on its mirror image. Say, therefore, these molecules are said to be chiral or dissymmetric, and does not possess any element of symmetry, and hence it is optically active. Right? This is optically active. This is also optically active. Structure for those, they will also show a optically active. It is Fisher projection formulas of lactic acid. The horizontal line they will show is above the plane of paper, and group's vertical line they will show below the plane of the paper. And hence Fisher projection formula can be drawn as like this. So those molecules of Fisher projections and those molecules of the Fisher projections, they are similar. Also, they are superimposable on its mirror image. Non-superimposable mirror image. So this is called as this molecule shows chiral molecules and optically active. Now we are going to discuss enoisomers. Enoisomers, it means the stereoisomers which are non-superimposable mirror image of each other, and they rotate the plane of polarizer light through a same angle but in opposite direction. It is called as enoisomer or enoisomorphism. Right? What is meant by enoisomers? Enoisomers are the stereoisomers are non-superimposable mirror image and rotate the plane polarizer light through a same angle but opposite direction. This is called as a enoisomorphism. For example, this is a 2-fluorobutane. It is these two molecules which are the non-superimposable in its mirror image. One is a D form, other is a L form of these isomers. Now we have seen some characteristics of enoisomers. First is they rotate plane polar light to the same plane but in opposite direction. Second characteristics, the pair of enoisomers is formed. One is a dextro-rotatory, can be designated as small d or plus sign, and other is a levorotatory, which is designated as small l or negative sign. They have the same physical properties. Next characteristics, the enoisomers have different physiological activities. Now next points we have discussed the racemic mixture, some characteristics for racemic mixture as like the mixture containing D and L forms, but these D and L forms which are optically active compounds in equal amount. This is called racemic mixture. It means 50% retention and 50% inversions, or 50% levorotatory, 50% dextrorotatory. It is optically inactive. Racemic mixtures are optically inactive. Racemic mixture, it is represented by DL or this sign, plus minus sign of the. Now we have discussed the stereochemistry of carbon compounds with two dissimilar asymmetric carbon atoms. Two dissymmetric carbon atoms, the number of stereoisomers formed, given the formula is 2 raised to n. N means how much numbers of asymmetric carbons or how many number of chiral carbons. Now see these compounds or these structures which shows two chiral carbons. This is one, this is second chiral. So two chiral carbons, so four isomers are possible. So these four isomers are one of shows the erythro forms. It means the two groups which are same side, so erythro and its mirror image like this. Similarly, it is a 3O compounds. The 3O compounds means two similar groups which are opposite side and its mirror image. So four isomers are possible. For examples, we have take these examples. So how many chiral centers? Like 3 bromobutane 2 all, right? 3 bromobutane 3 bromobutane 2 all. It is 2 chiral centers. This is a one chiral center and this is a second chiral center. So four isomers are possible, one of which the erythro form, right? So two hydrogens which are same side, so erythro form. So its mirror image for these. And secondly, it is a 3O compounds. So similar groups which are opposite side. So it is a 3O and its mirror image. So four isomers are possible due to two chiral center.